Have you ever found yourself staring at the back of a fuel truck on the highway and wondering why it's round instead of boxy? That curved, cylindrical tanker design isn't just for aesthetics. It's hiding some fascinating science that could mean the difference between safety and disaster. In this video, we'll reveal why these massive vessels of flammable liquid aren't shaped like the rectangular cargo trucks you see everywhere else. The answer involves physics, fluid dynamics, and surprisingly practical engineering that affects everything from how the truck handles to what happens in a catastrophic accident. The physics behind cylindrical tanks, when science meets trucks. Have you ever watched a coffee slosh around during a bumpy car ride? That's inertia at work, only on a scale that can tip a truck over. The cylindrical shape of these massive fuel tankers cruising down the highways is carefully engineered based on fundamental fluid dynamics principles. When a tanker truck carrying thousands of gallons of fuel needs to brake suddenly or swerve to avoid an obstacle, the liquid payload continues moving forward due to inertia, creating powerful waves that push against the container walls. This liquid momentum generates tremendous force, enough to tip over a large vehicle, if not adequately managed, potentially. In rectangular tanks, this sloshing creates unbalanced dynamic loads. When a liquid hits a flat wall, it creates a powerful pressure spike and then rebounds, often creating a standing wave that oscillates back and forth. It's like watching stadium fans do the wave, but with dangerous consequences. The liquid's center of mass shifts dramatically, effectively pushing the entire vehicle in alternating directions. Why cylinders win? Physics in action. Let's see how the cylinder turns chaos into calm by dispersing energy around its curve. When liquid sloshes inside a cylinder, the curved walls simultaneously redirect the energy in multiple directions. Instead of creating powerful, unidirectional waves, the cylinder disperses the energy along its circumference. This creates smaller, counter-rotating currents that effectively cancel each other out, neutralizing much of the dangerous motion. At the microscopic level, the difference becomes even more evident. In square containers, liquid molecules slam against flat surfaces and rebound with most of their energy intact. Cylindrical surfaces, however, create boundary layer effects. Imagine how sound travels evenly around a circular stadium rather than bouncing back from a flat wall, where the curved geometry naturally dissipates kinetic energy through increased turbulence and friction. In real-world tests, engineers observed that rectangular tanks suffered pressure spikes up to 3 times higher than cylinders. Imagine a 30-ton push trying to shunt a truck off course. Rectangular tanks experienced lateral forces strong enough to shift a vehicle's center of gravity beyond its stability threshold, while cylindrical tanks maintained safe operating parameters. Strength by design, built to withstand pressure. The pressure distribution advantage extends beyond just sloshing. Static pressure from the liquid's weight presses equally in all directions, but rectangular tanks concentrate this stress at corners and seams. These junction points become natural failure points where metal fatigue occurs. Cylindrical designs eliminate these structural weak points by distributing pressure evenly across the entire surface, similar to how an arch in architecture can support enormous weight. This principle explains why submarines use cylindrical pressure hulls. At extreme ocean depths, the water pressure would crush a square vessel by concentrating forces on flat surfaces, while cylindrical designs distribute these enormous pressures effectively. The cylindrical shape creates inherently self-dampening wave patterns. When liquid moves in a circular container, each wave naturally generates counter waves that propagate around the circumference. These waves interfere with each other in a pattern that resembles ripples in a pond, but they tend to cancel rather than amplify each other's energy. Structural integrity and safety standards. Safety is the #1 priority. While preventing liquid movement makes tankers safer during everyday driving, what happens when disaster strikes? In the split-second chaos of a highway collision, the difference between cylindrical and rectangular tanks isn't just about stability. It's measured in lives saved and communities protected. Every day, thousands of fuel tankers navigate through dense traffic carrying what amounts to mobile bombs, up to 11,500 gallons of highly flammable liquid. When these vehicles crash, the tank tank's structural integrity becomes the only barrier between a manageable accident and a catastrophic explosion. This is where the cylindrical design proves its worth beyond sloshing prevention. Impact forces from a collision behave similarly to hydraulic pressure, seeking the path of least resistance. In rectangular tanks, these forces concentrate at the corners and seams, where structural failure is most likely. Think of it like cracking an egg. It first breaks at its sharpest points. A cylindrical tank, however, redirects impact energy around its curved surface, dissipating the force rather than allowing it to concentrate in any single area. This principle was tragically demonstrated in the 1973 Kingman, Arizona disaster. A propane tanker with rectangular sections was involved in a railroad crossing accident, leading to a catastrophic explosion that killed 11 firefighters and injured nearly 100 others. The rupture began exactly as engineers predicted, at a seam where two flat surfaces met. This and several similar accidents throughout the 1970s catalyzed comprehensive regulatory reform. Regulations. In response, the U.S. Department of Transportation developed the first modern safety standards for hazardous material transportation. Regulation 49 CFR specifically mandates cylindrical designs for most flammable liquids, with detailed requirements for wall thickness, material composition, and pressure testing. European regulations followed suit with ADR standards, European Agreement concerning the international carriage of dangerous goods by road, creating a global consensus on tanker design. These aren't just bureaucratic paperwork, engineering requirements written in blood. Compliance tests are brutal. Tanks must withstand being dropped from specific heights, exposed to open flames for prescribed periods, and subjected to puncture attempts from standardized equipment. Only designs that can maintain their integrity under these extreme conditions receive certification. The data supports these regulations. Studies comparing pre-regulation tankers with modern cylindrical designs shows a reduction in post-accident fire and explosion rates by approximately 25%. This translates to hundreds of lives saved since implementation. When accidents occur, cylindrical tanks are more likely to remain intact or sustain more minor, manageable breaches rather than catastrophic failure. Cleaner, cheaper, safer. Cylinders do it all. An often overlooked benefit of the cylindrical design emerges during routine maintenance. Rectangular trucks develop hidden corners where residual materials can accumulate over time, creating cleaning challenges and potential chemical reactions. Cylindrical tanks allow more effective cleaning procedures using automated systems that can reach every internal surface. This reduces contamination risk between loads and extends the operational lifespan of the equipment. There's an economic dimension to these safety features as well. The cylindrical tank's aerodynamic efficiency creates 5 to 7% fuel savings compared to box-shaped alternatives. A tanker traveling 100,000 miles annually represents approximately $20,000 to $30,000 in fuel cost savings per vehicle each year. With fleets often numbering in the hundreds, major transportation companies save millions annually while simultaneously operating safer vehicles. Insurance costs reflect these safety improvements too. Premiums for hazardous materials transportation have decreased relative to inflation since the implementation of cylindrical tank regulations, despite the increasing value of the vehicles and cargoes being insured. Insurance actuaries have cold-heartedly calculated what engineers already knew. Cylindrical tanks save money and lives. The regulatory standards continue to evolve. Modern tankers incorporate additional safety features like reinforced baffles, specialized pressure relief valves, and advanced materials that build upon the fundamental cylindrical design. Some cutting-edge tankers even utilize double hull construction for hazardous materials, creating a redundant safety system inspired by maritime oil tankers. So, what have we learned? The roundness of fuel tankers isn't just clever engineering. It's a remarkable example of how form perfectly follows function. These cylindrical marvels represent the intersection where physics, safety regulations, and economic efficiency all point to the same design solution. Next time you're driving alongside one of these gleaming silver tubes on the highway, you'll appreciate the invisible forces at work keeping that volatile payload secure. It's a testament to human ingenuity that something something so seemingly simple required decades of research, tragic lessons, and scientific innovation to perfect? What other everyday objects around you hide similar stories of brilliant design? Let us know in the comments and subscribe to the channel for more videos like this.